All right, so hi, I'm Andy. I'm a senior in computer science. Some of you might have known me as a former exec for Michigan Hackers. I worked on MX for several of them in the past. And I'm also our campus ambassador for Facebook, because Facebook is an awesome place to work, and I'll be going there after I graduate. That's a box of swag from Facebook. After the talk, we will be distributing that amongst those of you who are willing to brave the whole thing. So if you like, we have like t-shirts, buttons, cards, charger things that are awesome. So stick around. So what am I talking about? I'm talking about advanced topics in templates. Aren't those a doozy? So more specifically, first, I'm going to talk about the basics of C++ templates. How many of you actually are in 280 or taken 280 already? Okay, has anyone not taken 280? How's that? Okay, you guys might have a hard time, but I'm going to try to make this as clear to you guys as possible. So I'm then going to talk about the basics of template metaprogramming. Template metaprogramming, that's a big word, and we'll spend some time deciphering exactly what you can do with that. Then we got variadic templates. That's another cool topic. Everybody loves variadic templates. And then we're going to make a tuple example, and this is going to be a really basic tuple example, but even when I say basic for a tuple, it's still going to be really cool, and we're going to have to dive right in, and it'll be fun. Ask questions. This is complicated stuff, and if I don't explain this well enough for you the first time, say, I really need help, and I'll explain it again. Actually, everybody, look to the person on your left.
Which side is that?
Well, if you raise your left, yeah, anyway, so that person will have a question if you have a question. So if you think that you're the only one, you're not, because whoever's to your left also has that question. So ask your question.
Yeah, basically. That is your left, right?
All right. Okay, so let's talk about super basic template usage. What do I have here? I got a function that does some math. It takes an int and another int. One is 3, one is -3. And I'm asserting that the absolute values of those are the same. That makes sense, right? The absolute value of -3 should be 3. So that should work. Now, when you see that abs function, what does that look like? It looks like the sort of thing that'll take an int and return an int. And that should be simple. But what if I want to do it with a different sort of numbers? We got doubles. Doubles are numbers too, but doubles aren't ints. Here I have just a 4 and a -4, and like with integers, the absolute value of the negative of double should be the same. So this is something called a template in C++. What a template lets you do is write a function once that'll work across all sorts of different types. How is this going to work here? I wish this was a bit lower so I could point easier. I have this funny thing that doesn't help very much. So the top line there, it says template type name T. The template line is saying that the thing below it is going to be templated. There's going to be some instance where the compiler is going to have to do some work to figure out what types are going to have to go where. And that T is saying that whenever I see a T, it's going to be a type that'll be substituted in by the compiler. The function returns a T, takes a T, and then it does the basic absolute value math. If the number is less than 0, it flips it, and if not, it returns that. Now that logic will work with an int, that logic will work with a double. And because of that, we're able to write this templated code that if I call abs with a double or abs with an int, this is going to compile, those assert statements are going to work. This should be familiar to most of you, right? Those of you who haven't taken 280, does that make sense? All right. So templates, that's a templated function. You can also do templates over objects. This is a simple pair structure that I'm calling. And what does a pair do? It holds a first element and a second element. And this could be anything. I could have an int and a double. I could have a double and a string. I just want to be able to put two things together. Now over here we see I have template with two type names. I have a t first and a t second. Because those types, they don't have to be the same. And then my first is of the type t first, my second is of the type t second. And over here we see that I'm making a simple pair. I use these angle braces to denote to the compiler what I want to put in my templates. Here I'm putting an int and a double, and then there you have an int and a double. Here I have a string and an int. And when I print out what these have, I got, in the first instance, that the int and the double is in foo, and that lemons and 42 are in bar. That's clear. Yes? So templates work in structs. Templates also work with things other than types. A lot of the times you learn about templating something over a type, but here I can template this over a size t, or a number. What is this going to do? I see it says template size t number of copies. That size t is going to be a parameter that I put in at compile time. See, through the brackets, I'm putting a number. And it's going to treat that just as any other compile time parameter might. The compiler knows to fill that in. So inside the thing, that's a loop that you might see normally. For the I is 0, as long as the I is less than the number of copies, increment I. And I'm going to print that 3 times if I put the 3 here. So I could have just as easily, where I have size t there, I could have written int, I could have written double. For those of you who might not know specifically what a size t is, it's an unsigned number that is of the size of one memory address. So it's sort of the thing that the compiler can most efficiently manipulate math with, and it's an unsigned type. So that could say unsigned int. It's important to tell the compiler what exactly I'm putting in the template. If I were to say type name there, number of copies, that's a number. Numbers aren't types. I need to be denoting that it's some sort of a number here. And I'm using size t in this case. Yes?
Is this kind of usage C++11 specific, or is it?
No. You could template over numbers all the way back to C++98.
Auto.
Yeah, the word auto. Has anyone seen that before? Has anyone not seen the word auto before? Yeah, so normally inside the for loop, I would say something like int I equals 0. All the auto does is it says, look on the other side of the equal sign, whatever type that is, pretend that I wrote that type in. So here it's going to see that 0 is an int or a long, and it's going to say int I equals 0 for me. You put the auto there because that lets the compiler do what it can do best with for the memory efficiency. And because if you use auto consistently, you don't have to worry about if you change something, it gets filled in. So here we see once more, I'm calling copy print with this compile time parameter in the braces. The thing that's going to be put in is number of copies, and printing the team 3 times. We got Shem Beckler saying the team, the team, the team. We fired home, so that's exciting. So who uses templates? Those of you in 280 use templates. How many of you have used templates after 280? Okay, yeah, so you use templates, I use templates. The standard template library uses templates. The STL has a lot of containers that are useful. Here's an example of the standard vector. It has 1 template. This is a vector over int. I have a map, which takes 2 templates, int and char. And then this is a standard array. That's a new C++11 container. And that takes ints, showing that I'm putting ints, and also the number 3. Standard array, for those of you who may not have seen this new magic, it's basically a wrapper around the C array that lets you get the iterator interface, and it knows its size daily.
What's a map?
What is a map? A map is a set of key value pairs. Here I'm basically just showing it because it is something that can be templated over 2 types. Any questions here? All right. So those are basic templates. I got reflection time 0. So if anyone needs any bit on the basic templates, because right now we're like on the river, and now we're gonna go right down the waterfall, or down the rapids, or something exciting.
Do the numbers, like when you said 3, is a good compile time constant?
I'm sorry?
Like when you say array and 3, you have to be a compile time constant?
Yeah, notice how it's in these angle brackets, which means it's a compile time parameter. Everything that you stick inside of a template has to be knowable or known at compile time. You can't have things changing there. So this array, it'll be like saying with a C array, like int open bracket 3 close bracket. Yes?
With the new like bracket initializers and does that stuff have to be compiled time too?
Don't worry too much about that right now. I'm basically just showing here that you can stick the 1, 2, 3 in it. You could, if you're asking specifically about this array, populate it using the normal bracket syntax or with iterators as normally.
And you could put runtime information in the early versions.
Okay, so let's go into template metaprogramming. That's a lot of words. I picked that out of Wikipedia. Don't read all those words. We have some fewer words. So template metaprogramming is basically getting the compiler to use templates to do things for you, to write code that may be doing math. In fact, template metaprogramming in C++, you can use templates to act as its own functional programming language. You don't need to know what a functional programming language is, but it's complicated and it's fun and it's cool. And we're going to just do some basic math with it right now. So people know what factorial is, right? And factorial, it's the multiplication of everything, including n below n. So this is probably the first sort of recursive thing you learned, or the first example you learned when you were doing recursion. factorial event, it has a simple recursive definition, and then it has that base case. Now, if I were to write just normal code that would be executed at runtime, it would look something like this. I have a function, takes a number, use the base case. If it's 0, return 1. If not, I have the recursive definition. And over here, it prints out factorials of 2, 3, 4, and 5 with the 2, 6, 24, and 120. And that, it's doing what you would think it, right? This is code you'd expect. We can do the same sort of things with templates at compile time. This is sort of this is a test. This is the code that'll execute before I show you how to do it. Notice I have the factorial with the angle braces saying something's happening at compile time. And then I have that colon value. We'll talk about that in a bit. But it is printing the same thing. And also, this static assert, it's a bit different than a normal assert in that when your code is compiling, the compiler will actually check to make sure that this is true. So if there is a factorial math problem, that string will be the compile error you get for this math not working. Now, let's look. I'll show you this again. But first, let's look at the code that makes this happen. So first, I'm going to do an incomplete declaration over a struct I'm calling fact. Now, a struct, you say, we were using functions earlier. One thing about templates in C++ is that the compiler doesn't do function calls during compile time, normally. What it can do, however, is create structs with values inside that have memory. So what would we have for a base case here? We see this first is templated over the size tn. That's the compile time parameter we're looking for. And if that n is 0, then we're going to have a value equal to 1. Now notice, this value is a member of the struct. I said we can't have a function returning something, so this is how we do it. We tell the compiler, put this in the memory for us to look up later. And it's a static variable, which is important, saying that it is going to be somewhere global at compile time, that the compiler knows where it is, and it's const, because this is a mathematical thing that's never going to change. You're never going to say that factorial of 0 is like 72. And how would we use this then is the recursive definition. Previously, we saw just the return event in that. Here we have the same template, size tn, and then we're returning the recursive definition. But here, once more, we have this colon value. That's saying that we need to look at that, access the number that is the value object, and do the math on that. And here, in our compile time argument, we're doing the n-1. So this is doing that same recursive math, but it's at compile time. And when we look over here again, we're going to see that we're printing out all the same stuff, and the static assert shows that the math is done at compile time before we run our code, and it will compile. Do I have any questions on any of that? Yes.
Can I go back to the code? Why is the base case?
Yeah.
Why doesn't the template declare anything?
That's great. I totally should have mentioned that. So this is something called partial specialization. If I want to say I have a template and I know that for one specific value I want to do something different. Here when we see 0, we want to do something different. I can just stick the 0 after the fact. Say that for factorial of 0, I want this to happen. And the reason I have those braces empty is because there are no templated values that I don't know about. Up here, I still have to say that it's templated so the compiler knows to deal with it. And I have to stick the empty brackets because that's part of the language's syntax. But there's nothing that's going to be variable in there. So I just stick the fact with the 0 there. Yes?
Does that work for types too? If you have, say, for double, you want to do something?
Yeah, this could work for types. If I was going to do something that would maybe do something with math, but for doubles I want to make sure that I have precision built in with my implementation, I could totally have a function that works for everything, but for doubles, do this partial specialization technique to have that fancy implementation there.
I think that the STL, you did vector bool or something, you would try to optimize it to a bit vector. Is that how they did this?
Yeah, vectors of bools, for those of you who know the STL, do have a different implementation that are much more memory efficient than it would have been if they didn't do the partial specialization. Yes?
Why are you using constexpr instead of constexpr?
Why am I using, okay, so constexpr is a bit different, and I'm going to actually talk about that a little bit here. But the thing that's important here is constexpr is the sort of thing that's going to be evaluated, and usually you use that as a function or a global variable. But here, this is a member variable, and actually, can constexpr work there?
I think it does.
Yeah.
Okay. constexpr will work there. Constexpr, though, does have some funky rules that won't always apply to the way you're doing it, and I'll sort of mention that in a few slides. All right. So if that is clear to everyone, I'm just going to go over another example, because this is like the sort of stuff that's cool that you're going to want to tell your friends. I can do math in compile time. So Fibonacci, you all know Fibonacci. 280 Project 2 still has Fibonacci, right? Yeah. So Fibonacci, you have two base cases, the 0 and the 1. The sequence starts out 1, 1, 2, 3, 5. And then you have your recursive definition that has the n-1 and the n-2. And how that looks in normal code, this is normal code, your base case. I'm doing the less than equal to 1, and your recursive definition. Now, who can guess? What am I going to have after this? Zero, blah, blah, blah. Sounds good. All right, so my base cases. I have a partial specialization for 0, blah, 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 and for 1, blah, blah, blah. Now notice, in the previous one, I had, in my normal runtime code, the less than or equal to 1. With templates, you can't say that. I can't say, for all of the things where the template parameter is less than 1, do this specialization, and if not, do the normal code. I have to say, sort of like in a switch case statement, I have to explicitly say, for 0, do this, for 1, do this. And even though their values are going to be the same, I still have to have those on 2 lines. And then the recursive definition is going to be the math. We got the n-1 value, the n-2 value. And then once more to iterate, the reason we have to have that : value is because if I just ask for my struct of n-1, that's going to be a struct. That's not going to be the number that I'm looking for. So, is that a question?
Yes.
Yes.
So if I just create a fib, say fib5, does it actually try to construct an object fib4 and fib3?
Yeah, why don't I go over that, sort of? So I call fib5 with the : value. I'm just going to say v because I ran out of space. It's going to go over here. It's going to go over here, and it's going to say, how do I calculate value? I need a fib of 4 and a fib of 3. So it's going to make that fib of 4. I'm left-handed, I apologize. I was born this way. And what's it need for the fib 4? The fib 4, it's going to need the fib 3. And that will need the fib 2. And the 1. Which will need the 0. Now, anyone know where I find the 0? Or actually the 1, too. Yeah. So yeah, we already know that. So this is going to be 1. This will be 1. So to calculate the 2, that's what's 1 plus 1? 1 plus 1 is 2. So 1, 1, 2. When it looks here, it'll look up 2 and 1. And when I said earlier it memoizes, that basically just means that the compiler is going to keep these around, so it doesn't have to create them again every time. It just says, what do I have here? I have this. So 1 and 2 is 3. That's not what we. That's better. My hand's blue now. 3 and 2 is 5. And this then is going to be 5 and 3, which is A. D8, yeah.
So does the compiler destroy 4, 3, 2, 1, 0 after getting 5, 1?
Yeah, the compiler is actually really good at optimizing this. So the stuff that it's going to need, it'll be able to say, I need this. And the stuff that it doesn't, I think it's going to be able to get rid of. Yeah. Was that a question in the back I saw?
I was just going to say that's like important enough to using static variables, so you're not actually constructing objects for fib, like a runtime object.
Yeah, no, this is, that's important. These are compile time objects. During runtime, I'm basically just going to be looking up in memory, right here, there's an 8. So I'm going to find that 8. And that's why this is so cool. I don't have to do any of this math at runtime. So when I'm executing my code, chugging along in the autograder, it doesn't need to calculate this. Anything else? Yes?
Is there any sort of elegant workaround if you have a lot of base cases?
If you have a lot of base cases, then you're going to have a lot of writing. No, there is no real elegant.
Enable this with conditionals.
Yeah.
Oh, hardly elegant.
There is an inelegant solution that is so inelegant, I decided to leave it out of this talk. If you look up enable_if, you can read up about it, but it's the sort of thing that you're definitely not going to have to need to do anytime soon. Anytime soon, at least. Yeah, so that was the Fibonacci example. Once more, I did this on the board, but I got the math. It's going to print out 1, 1, 2, 3, 5. I forgot to switch the outputs around. It should print out 1, 2, 3, 5, 8. And it will compile. The static assert. That won't work. That won't compile. 5 is 8.
Yeah.
See, this is what I get when I change the colors around and forget to copy things funny. Yeah, so here's an example for home. You guys have all done some sort of probability in high school, maybe.
Oh, no.
N choose R, N choose K. Figure this out, like late at night, you're thinking, wow, that was a fun talk, but I wish I remembered how to do it. Figure out with this problem, because the answer isn't here spelled out for you. Oh, yeah. Mark wants me to tell you about that one time I had to actually solve this at Facebook. Over the summer, I was doing something where I needed to loop over something, or loop over a loop, execute it for every possible combination of something that the loop was executing. And I ended up, instead of having to calculate the loop variable at runtime, using the solution to this template metaprogramming technique to figure that out at compile time. Now, I didn't have to do that at compile time. Or I didn't have to do that with templates. You mentioned constexprs. Constexpr is another way to do things, to do math like this at compile time. It's not the focus of this talk. So I'm only going to touch on it a little bit, and just know that it exists and that it's probably more readable than this fancy template code, but it isn't as cool. So let's do that fib example we just saw with our constext. All right, so here's a fib function done at the constexpr. Notice how it looks exactly like that first implementation we had, but instead of just saying that it returns a size t, it's a constexpr. That just tells the compiler, this is a function that you can execute at compile time and you can get the math done. And it's not going to have any side effects. There are a few rules for a constexpr. One of them is that it can't be having any side effects outside. If I had a global variable this was modifying, the compiler would say, no, that is not a constexpr function. And another one of those rules depends on what version of C++ you're using. You see, this code will not work on your Kane compilers. This is code that will work only in C++ 14 if you have GCC 4.9 and above. C++ 11 only lets you have one statement in a constexpr function. So if we want to have that if, we have to use the ternary operator to get this funky, not as pretty syntax. So here's our little last bit of constexpr. We have a static assert that, oh, I got it right. Fib of 4 is 5. That'll compile, or else we get the compile time math error. And in our example, these are actually done at runtime. The same code that we use in the constexpr can be compile time or runtime, depending on how you call it. The static asserts are always compile time, so that'll be done before you finish compiling. And the example function will be executed whenever you call that in your runtime code.
Wait,
Question?
what?
So you said if you did CPP 11 within the cout statement, that's going to be done at runtime?
Yeah, okay, so
Is
this,
it going to look it up at runtime, or is it going to re-go through everything and just going to do that?
this is actually going to do the math at runtime. You're not creating that big table, because if I see how I have that 4 there?
Yeah.
That 4 could be the return of another function, like get my number, and it returns the 4, and that could change based on various runtime parameters. So there's no guarantee to the compiler that when you do this at runtime, it's going to be able to look it up in the table. If I had the templated function with the brackets, template brackets, those are always compile time constants. So that's how you know. All right, so any more questions, comments? Reflection time 1. That was like basic template metaprogramming math. The talk once more is on template, so I don't want to get too focused on the constexpr stuff. So next, we have variadic templates. Variadic is a smaller word than metaprogramming. What is a variadic template? Well, first, let's talk about a variadic function. How many of you have never seen printf before? Okay, so 2, 3 of you. Printf is basically how you print things in C before you had cout with the fancy operator overloading and the type, or in the function overloading and everything. So printf, what it does is it has two arguments. The first argument is a format string. This is the type of a C string, const char star. And the second argument is this dot dot dot. We'll get to that in a sec, but note, that dot dot dot, that denotes that this is a variadic function. And it is not type safe. We'll get to that, but just note, it's dangerous. So here's me printing something. I want to print something. First, I want to print my number, 42. I got %d problems. The way that printf is implemented, %d problems, yeah. So that %d is something that the printf implementation knows. When I see %d, I'm going to look for something that is of type, something with a digit, so an int or a long. And over here I have my number. My number, I use auto, that'll probably be a long based on the compiler. Think about it like an int. But it'll fit it in, so it prints, I have 42 problems. Now
No, prints, I have 42 amendments.
the next one.
Oh, never mind, sorry.
Yeah, the top line is 42 problems. This print something one has my number and what I have, two variables. What I have is going to be a C string, a const char star, and it's going to be denoted by this %s. Whoever implemented printf, or I guess by committee when they decided how this worked, they have in the printf code something that looks, I see a %d. The first thing's going to be an int. I see a %s. There's going to be a string after that. And here, I have my number, an int, what I have, a C string. That's really, really funky and dangerous. What if instead of putting just a normal string like lemons there, I put in the number 17? The compiler doesn't know that 17 is going to be an int and not a C string, even though the auto would do that. But the printf, that would see, I have a thing, 17. I'm looking for a pointer, because that's how C strings work. But when I go to memory address 17, are you going to get lemons? I don't know what's at memory address 17, but it's probably not lemons. Yeah. So this is the sort of thing you would have as a security vulnerability. This could cause your code to crash. It can cause your code to do undefined behavior. It's bad and it's dangerous. And we really want to be able to use our compiler to determine if our arguments to things like this are safe and what we expect. So come variadic templates. More template stuff. Yay. So variadic templates is a way for you to have an unspecified number of template arguments. Over here, we had, where the dot 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 was, an unspecified number of other arguments. We had the my number, we had my number and what I have, that's one argument, that's two arguments. And in the code, you have to cast those so that you interpret them as you expect. With templates, when you use a variadic template, the compiler is going to know what you have. You're not going to have to do that work yourself. So you can maintain some of that type safety. You don't have to typecast, and the compiler will give you errors if things really aren't working out for some reason. So how can we use a variadic templates? Here's a basic example. I want to print some stuff. Over here, I'm going to want to print 3, 3.3, foo, and 42. How does that work in the code? You see I have here 4 things, but up here, what do I have up there? Wow. I have 2 templates. I have a first, and I have the rest. For those of you who've done 280, this should remind you once more of those list T's in that project too. You have a first, you have a rest, you have a head, you have a tail. It's going to print the first, and then it's going to call print stuff again with the rest. This is recursive again. If I have those 4 arguments, this will be the first, these will be the rest. I call it again, this is the first, these are the rest. This is the first, that's the rest. This is the first, and there is no rest. And when there is no rest, I go up to the very top where I print stuff with nothing, and that just gives us the new line, and it returns. So let's talk a bit more about that dot, dot, dot. That's called denoting a parameter pack in variadic template land. Parameter packs can be 0 or more arguments. If you remember, when I had that 42 as the first and nothing as the rest was still a valid parameter pack, even though it was empty. When I declare a parameter pack, I'm going to say dot, 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 followed by my type alias. So here I go template, type name, dot, 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 args. Args is going to be the thing that we refer to as our parameter pack. And then when I go to expand it, when I go to say I have all these parameters, but I want to look at them individually, I'm going to have the args followed by the dot, dot, dot. and here I'm calling it my args. If I want to call a function with my args that were previously declared as a parameter pack, I'm going to expand it here so that bar sees all of those parameters when I'm calling bar. So looking once more at that example, the example again, even, I have my print stuff with the first. The first is going to be one argument. The rest is a parameter pack, which is 0 or more arguments. When I look at it with the print stuff call, this is my first, so t first is going to be of type int, and t rest is the parameter pack containing the type of 3.3, the type of foo, and the type of 42. David?
Does this happen recursively, or do you do it like iterating through the parameter pack?
There is no way to iterate through a parameter pack like that.
So you have to do it
Pretty much. But since, yeah, Max?
What's going on in this case?
Let's go to the base case. Okay, so I'm going to go through this again, and that should hopefully clear it up. So I'm starting 3 is my t first. This is the parameter pack I'm calling t rest, the rest of the types. So I'm printing out the first value, which is of type t first. So first is a 3, t first is the type of 3, so probably an int. Then I'm calling it with rest. But I'm doing, notice the dot, dot, dot. That's unpacking the parameter pack. So instead of just seeing it as one thing, this call will see rest as a double, a C string, and an int. So I'm calling it again. First becomes the double, first becomes the double. The types of rest is C string and int. It calls it again. Foo is the first. 42, that's all the things in the parameter pack. That's one thing, that's all right. When I call it for the final time, 42 is the first, and rest is empty. So when I go to expand rest, it's going to expand to no parameters. There are no types in that parameter pack when I'm expanding it the last time. And this is then just a simple function overload. When I call print stuff with no arguments, then it's going to just print the new line. Yes?
So what does the type safety come into play here? Like, why is this better than just printf? Or printf?
Why is this better than printf? Here, the compiler knows all these types.
Okay,
The
so
compiler is going to
t
know.
first will become type int for the
Yeah.
first call.
Yeah, because this is a template, the t first, it's going to see that's an int. I know how to print an int. I don't have to do any conversions to something that I know how to print. So all the way through, the compiler knows all of these types. You're not going to have to do any conversions yourself.
Yeah.
And the compiler knows how to treat these.
So would you ever get a type mismatch using this kind of thing? Like, because the compiler determines what type it is it int, right? And then CL will know what it's a type that I want to print that out and
Yeah.
it'll do it correctly.
Mhm.
Right, so you can't make a mistake. You know what I'm saying?
If you wanted to make mistakes and you tried hard enough, you probably could. But as with anything in C++, but usually you're going to be pretty safe doing this. And I saw a question over there.
But so like in C++, when you call printf, it's not doing this, it's just doing the original C.
Yeah. The printf is actually probably the code that your C++ is looking at is code from your computer's implementation of the C standard library, which links properly with C++.
So they didn't like decide to rewrite printf for C++.
No.
Made it safe.
No, hopefully by now, I don't know, how long has printf been in existence? Like 30, 40, 50 years? They should have gotten an implementation that works. But if you're writing, you never know. I mean, Heartbleed, right? But if you're writing your own code that uses a variadic function, chances are you're going to find some way to fit a bug in it, even if you're not looking at that. And these variadic templates will help you not. Yes?
Are those functions available at compile time, or this is in runtime that they find those overloaded functions to?
Yeah, that's going to be a runtime function overload.
Okay.
Yeah. In fact, the base case print stuff, that's not even templated over anything. So all the compiler knows is to put that in its function table. And then at runtime, it's going to look it up and it's going to find it, and we're going to be happy. All right. So any more questions? Yeah, my high school computer science teacher, questions, comments, cries of anguish? So anything else on sort of the basics of how to use a Variadic template? All right, so we've got about half an hour left. We're going to go into our tuple example. Woo! Boom, yeah. So you remember earlier, you saw that pair function, or the pair struct that we made. It had a first, it had a second, and those could have been over any type. What if I want more than two, though? what if I want 3 or 5 or 27, but I don't want to have to write a new struct for each of those. I want the compiler to be able to say, I have these types, I know a struct, I can compile that has this amount of types. Well, with variadic templates, we can make a tuple that'll have any number of things of any number of types. So what do we want? Intense, yeah. All right, what do we want in our tuple? We want it to have any combination of types. I could have something with all ints, but that's boring. Or I could have something with an int and a string and an octopus. Yeah, octopus objects, those are exciting. I don't want to have to, at runtime, do any of that conversion to get type conversion based on programmer implemented type conversion stuff, because that's dangerous and that's funky. We don't need that, because we have a compiler that can do all that for us. And then finally, I'm going to write a get function that will let us access the elements in our tuple. All right, so what do we want our tuple to do? We want it to pass some basic tests. I want to be able to make a tuple. This tuple has an int and a char in it. It's going to be able to use the get function once more to access the position in the tuple we want. So when I go get of 0, 0 is that compile time parameter of my tuple, that's going to access the first memory element in my tuple, the int element, and I'm going to assign a 32 to it. When I do get of 1, that's going to give us the 1th position, which will assign our character to it. And just like I'm assigning 2, I want to be able to read from. So I have the value 1, the value 2 that I'm getting out of the tuple, and I'm asserting that they are what I think they are.
So is it not possible to say overload an operator like square brackets in this scenario? Or because I'm just assuming you use a very similar thing but without it?
Yeah, this is the sort of thing. Notice how those are compile time parameters. That's a templated number in there.
Yeah.
So we're going to actually be doing some compile time work to access that position in our tuple. And we're going to go over that over the next few slides. All right, so you see anything ugly here? I mean, probably a lot of it. I don't really like that comment color. But over there, I have to say tuple of int and char and then assign to it. That's kind of ugly right there, see? I have to tell them what the types are. When I made that function earlier, that print stuff function or whatever, I didn't have to tell it, this is print stuff of int and double and string. The compiler was able to deduce the types and figure that out. There is one problem, though, with compiler template type deduction. It doesn't work on constructors. With the C++ language, you can only have compiler type deduction on functions. It's actually, due to some technicalities, impossible to get that to work on type constructors and have all the overloading work. So we're going to want to make a function that we can use to give us a tuple that'll have the types in it we want. And let's call that our make tuple function. So we're going to make a tuple. And what are we going to want our make tuple to do, to look like? Another basic test to pass. Basically, I'm going to have my T2, that tuple, that is the return of my make tuple, and I'm going to call it with a 64, an H, and a string. That's a standard string, and I'm making it explicit. I want to be able to put an object in there too, not just basic types. And then the get function should say that at the positions where I want them to be, those values are. So that's what I'm going to want my make tuple to do. And we'll get to this in a few slides again. But first, let's talk about implementing that tuple. So as we had earlier, this is going to be sort of a recursive style thing. And I'm going to have, to write this tuple out, my T types, my tuple types, is a variadic parameter pack. So it could be 0 or more. And that's the incomplete definition of my tuple. Now, what's sort of the base case for a tuple going to look like? Well, yes, one parameter, and that's going to be in the 0th position.
Oh.
So yeah, that's right. So I'm going to, or actually no parameters. Yeah, no parameters, which is 0. Jay was right. I was wrong. Good job, Jay. So what does an empty tuple look like? Something that has nothing in it? Well, what do we not know about it? We don't know nothing. It is still templated, but what are the types? There are no types. Everything is set. So our compile time things, those brackets are going to be empty. We know that there's nothing in here. And even the body of our struct is empty. We're not holding any memory in there. It's an empty tuple. It shouldn't take up any memory. Now, what are we going to do? Yeah. What are we going to do for our recursive definition? what we're going to do is we're going to hold a value. And remember earlier, I have the first and the rest. It's templated over the first and the rest. And what's that? That looks like inheritance to me. Ooh, inheritance. Yeah, so those of you who haven't taken 280, I'm sorry.
Sparks the evil.
Yes. So, why are we inheriting? And what are we inheriting from? So, we have our value and the rest. This is our first and the rest. And here we're storing the first, and we're inheriting from a tuple with the rest. Now, in C++, when you inherit from another class, when you are a base class and there is a superclass above you, the memory for your base class and your superclass is going to be put all together. So, if I'm going to have this tuple of int char string, I'm going to have first. Int is the value, and the rest will be char string. So my value is going to be an int. And this box, this is going to be, that's the value you see. This is all that's in a tuple of int char string. But we can't have this alone, right? This isn't an int char string, this is just an int. So we have to put our parents here. When the rest is char string and we're inheriting from a tuple of the rest, when we look up a level, we see that the value is char and the rest is going to be string. So with value, the t value is, and draw another box, char, and I'm going here, I have a tuple of char string. Now, once more in the same way, we have char is our t value, the value of this in the tuple, and string is all that's in our t rest. So when we go up a level, we have t value being string, and our t rest is going to be empty. This here is just going to be a tuple of string. So we have our t value string, our t rest is empty. What happens when we inherit from a tuple of t rest? We have inheritance from the empty tuple. That's the base case. Arrow. So that goes here. No more memory. Yeah. So think about, just a sec. So think about it. These are like little cards here. Cards are on top of the other. So I have my string, that's going to be in the back. I have my char on top of that, and I have my int on top of that. So when I'm accessing, I have this tuple of int char string. When I try to access the dot value, these are shadowed, because this int is on top. This card is shadowing these. And what is shadowing? Shadowing is the term when you have inheritance and you have multiple things with the same name, and only the one at sort of the deepest level of inheritance, or the card on top, is the one that our dot value will access. Now, do you have a question? Did that help a bit?
Me, yes,
Yes.
because I thought that was box containing the box, not card on top of the card.
Think about it like card on top of a card, right? The tuple of int char string, I'm going to say, this is a tuple of, it inherits from a tuple of, which inherits from a tuple of.
Which inherits from?
Yeah.
Which inherits from the NG.
Which inherits from a tuple of nothing.
That's why box in the box.
Now let's just, for the sake of being able to refer to this, why don't I call this the int, the char, the string? This is my type T. And this is a tuple type T. So these are tuple type T's, this tuple of int char string, because when I have this, that's a tuple of int char string. And here, the type T is what the value is going to return. That's this int. Now, how is this going to work when I try to get values out of this? Actually, do I have any more questions on this first? No? All right. So how am I going to try to get values out of this? Well, the way that you would deal with this shadowing problem that we have, when I have a tuple of int char string, the value only gives me this int. I can't be like, yo, talk to the parent to give me that value. There's not a way to do that in C++. But what you can do is you can look at this block of memory as something else. You can do a static cast to see, I take off that card. If this isn't here, then I have a tuple of char string, and when I call the dot value, I get a char. So if I static cast this tuple right here into a tuple of char string and call the dot value on that, I'll be able to access the value at this char. And if I were to try to cast it to a tuple of just string, then I'd be able to access the value right here in memory. So this is memory, and these are the locations of the values of these types. Yes?
So what you're static casting, they basically throw the pop cards off.
Yeah, the compiler is able to say, I know how this works. When I static cast up the inheritance, I'll put those cards away for a while, and I'll look at what's under it. And I'm not going to do anything, I'm not changing the memory when I'm doing that static cast. Only the return type of that static cast will be something that'll have the dot value giving me the string here, or the char, depending on if I static cast to this or that. And if I were, let's say, to try to static cast it to this empty tuple and call dot value, that won't work, because there is no value element in our empty tuple. It's empty. All right, so how are we going to try to do this static cast? Well, let's say we have this get function that I remembered. The get function is going to be templated over the index, so I want the 0th, the 1th, or the 2th element. It's going to have our type. No, 0th, 1th, and 2th. You access it with the 0, the 1, and the 2. I want to be as explicit as possible here. And I'm returning. What am I returning? I'm returning something over here, right? I'm returning one of my type T's. But it's not just type T. It's a type T reference. And that's just going to say, when I return, I want to access this memory here. So if I want to assign to it, I'll be able to put that in this tuple instead of having to make the copy. The get function has a name, that's get, and it's going to take in our tuple. And it's of the T types ... Now, over here, I only have the tuple. I don't have the index. The index, as you saw in the example, is a compile time argument. I'm going to have to pass in the 0 or the 1 or the 2 at compile time like this. Get bracket 1 of my tuple, and I want to assign it to D, because that's a character. I can put that there, right? So inside the body of this, we're doing that static cast I was talking about. I'm going to have the tuple type T that I know. If I want this, the TFT being char, I want the tuple type T to be the tuple type T to be tuple of char string. That's going to do the conversion to a tuple of char string, the reference, just so that it's the same thing, of the tuple and get the dot value so I can access what is in this memory. Now, you see, there's some weird spacing here. That's because I've left out where I'm getting that tuple type T. In order to figure, that's important. So in order to get this data from here, I'm going to actually want a helper class. Yeah. Isn't this exciting? What have I done? I've made a tuple element. And what is a tuple element going to take? It's going to need the index, right? It needs to know how far it's going to have to go to give me these things. And it's going to need the tuple, the type of my tuple. So, the base case with our tuple element is going to be accessing the 0. When I have my tuple of int char string, I want to get, what do I want to get out of that? I want to get this here, the type T, and this here, the tuple type T. And what do I have over here? I have it specialized over the 0, saying that this is the base case. This is me just looking at the values as I can see them. And I have my tuple with the T value and the T rest. That should be familiar to you. What's a using statement? Who here has never heard of a using statement? Yeah, so of you who have never heard of a using statement, put your hands back up. Put your hands down if you have heard of a type def. Okay, so I have like 2 or 3 people who don't know what a type def is. A type def is a way to refer to something by a different name. That's an old, before C++ 11, like C had it, C++ 98 did. If I said something like type def balloons int, or type def int balloons. I always get the order messed up. But that would let me refer to anything with the word, when I say balloons, the compiler says, okay, I know what that is, that's an int. The reason why we have using statements is because type defs don't work with templates. Using statements do. And what do we have over here? We have a template. So we're going to use stuff. Also, using statements in C++11 is sort of deprecated type def. So if you have C++11 in your compiler, use things, don't type def them, or using the things. All right, so what am I doing here? I have a tuple element with a 0 and my tuple of t-value t-rest. That's going to be here my tuple of int char string. I want to get the type t. That's t-value. T-value is going to be the first in my tuple. What's the first in our tuple of int char string? That's going to be the int. That's our top card here, the int. That's our type t. We're saying it's our type t. Does that make sense to everybody? Okay, so what are we going to do next? We're going to say using tuple type t is a tuple with the value and the rest. Over here, our value is int, the rest is char string. Our tuple type t is a tuple of int char string. So our tuple type t, the using tuple type t just says we can refer with the word tuple type t to the type of tuple int char string. Good? Anyone not good? No? Okay. Yeah, tuple type t.
But the last 5 minutes of the talk, just say it as fast as possible. There's been work in between, but not as work.
All right. So this is how we access the 0th element. How are we going to do more? Well, following the pattern that we've seen, I got my incomplete declaration, I've got my base case.
I recurse.
Yeah, I'm going to recurse. I really love recursion. Here's our recursive tuple type or tuple elements definition. What's it going to take? It's going to take the index of what I want. It's going to take the t-value and the t-rest in the same way that our tuple is of t-value, t-rest that's passed into it. The index is passed into it. And what's this? This is a struct and it inherits again. Yay. So what are we going to do here? I have a tuple element of index -1 and a tuple of the t-rest. And it's not going to do anything. It's going to be empty. But it's going to inherit, so we're going to have to go up the chain. Now, how are we going to go up this chain? Let's say that I want to call with the index as 1. Over here, what does that expect? What do you want out of the 1 index? Char, yeah. So what we're going to do is we're going to say, index, go with -1, make a tuple of the t-rest. What's a tuple of the t-rest going to be? Char string, yeah. So we're going to have tuple of char string. We're going to have index of 1 - 1 is 0. That goes up here. We have 0, tuple of char string. What's our type t? And what's our tuple type t? Yeah. So using this inheritance, even though we're not necessarily going to be storing any of this in memory, this takes no memory. The using statements are just things to tell the compiler what to do. It doesn't store anything. But the compiler knows how to go up this chain to get the types we want. And what are we going to do with these in the get statement? We're going to say, I want this as a tuple of char string, so I can peel off the int card, call .value, and get my character. Now, once more, I'm going to go over this again. So let's say I want the second, or the 2th element. It's not the second. The 2th element. Index, yeah, the 2th. See, the 0th, the 1th, and the 2th.
That is right.
That was it.
Okay, whoever it was. Yeah, the 0th, the 1th, the 2th. So, how is this going to work out? We're going to start out, index is 2, the t-value is int, the rest is char string, index -1, get rid of the first one. We have tuple of char string, t-value is char, t-rest is string, index is 2 - 1 is 1, and then we're going to do it again, because we're here, because we're not at the 0. Index 1, what's 1 - 1? That'll end up bringing us to the 0 next with a tuple of t-rest. If this is char, this is string, the tuple of t-rest is going to be a tuple of string. And since that is at the 0th, our type t is the value here, which is string. And our tuple type t is a
Tuple of empty tuple.
tuple of string.
Wait.
Yeah.
Oh.
You know what string?
It's a tuple of the value and the rest.
Oh,
And because
okay.
the value is a string and the rest is empty, it's just going to be a tuple of string. So, is that clear? How we can go up and get the thing, the tuple type T that we need, so we can cast it by taking off these cards to what we want. All right, so let's look at our get function again with this filled in. We have it returning now, instead of just that type T that I wrote, it's a tuple element with the index and a tuple of our types, : type T, and then the reference that we had earlier. What's that type name keyword doing there? The type name keyword has to do with a really complicated language ambiguity that the compiler doesn't really need, but you have to put to be language correct. And if you don't have, the compiler will get mad at you. It basically says that when I'm accessing type T, this thing inside my tuple element, it's going to be a type. And let's say I'm doing get of 0. What's that type T going to be? Get of 0? What's this type? 0. Yeah. And then over here in the function, I'm going to say another using, just so I can have this here and this here. Ooh, over here now. So, you don't have to move the camera, I'm coming back. So I'm going to have once more my tuple element with the index and the tuple with all of its types. It's tuple type T. So that here, when I get, I say I want int, I can get tuple of int char string. When I do this static cast to the tuple of int char string, I look at the top card, that's an int, so that's the value that I'm going to be returning, the thing in this int memory. If I were to do it with the index is 1, I'm going to call get, where the index is 1, the tuple types, it's still int char string, but the tuple element is going to say, aha, the type T is the 1. So peel off the int card, type T is char. Over here, the tuple of type T. Look over here, and it's a tuple of char string. So when I cast this to a tuple of char string, when I peel off the card, I can call dot value and get the value in this char memory. Does that make sense to anybody? I said, does that make sense to anybody it doesn't make sense to? You're all lying.
Yeah.
Okay, maybe some of you are lying. He's heard me do the talk before. All right, if you insist. So when I call this, what's it going to do? Over here, I'm going to see, I want a char, the 1 makes the index 1, the tuple element will give me the char so that I can assign it where I want. Now, why don't we look over at that example? What do we have now that we have our get? Well, if we make the tuple of int char, I call get 0, what is it going to be converting my tuple to? What's it, the static cast? Tuple int char. Remember, with the 0, we're at the bottom already. This is the same as this, right? Because the 0th thing is always the top card. But when I go with the get of 1, it's going to peel off that card. So it's converting it to the tuple of char string. And there, I'm assigning the char.
So it would just be tuple to char.
There's no char string.
Tuple means char.
Oh yeah, over here, you're right, yes. I'm not using this one, I'm using that one. So it is just tuple of char, good catch. Then when we have, we're doing the same get call. This over here is behaving the same as it is over here. And because we're using the reference as the return type, it's going to be looking at the memory. So the memory we assign is the memory we're reading from. We can read from it, and I assert that this works. Thumbs ups? Anybody? Yeah, thumbs ups. Anybody thumbs downs?
I thumbs up. But
You have a thumbs down? Is that a lead to a question?
Yeah, that's me to a question. Can you go back to the get code?
You want the get code?
The code get, whatever.
Yeah, this code.
Which part of the code says that get can take in a templated number?
Over here, I have the size t index. Now remember, size t, that's an unsigned number type. So I could have written something like unsigned. I could have written unsigned long. I could have written, well, if I wrote an integer and tried to put a negative number here, that would just be funky. So I'm using unsigned types.
This might be really stupid, but do we have to like specify get 1, comma, the type name for t types? Because I don't fully understand template very well anyway, so.
Yeah. So just trying to show this again. So what my get call is going to look like, it's going to look like this. the compiler needs to know what position I'm looking for. So that's why I have to say the 1 here. That's a number that I'm giving to the compiler. That's the index. The t-types, the tuple types, I can infer or I can deduce from the type of my tuple. So I can say that the t-types in this example would be a parameter pack containing int char string.
Okay.
Yeah, so when I call it, this is passed at the compile time so it knows how to do the work, but it can do the work on any tuple as long as the type is right. So this is a runtime argument in the parentheses. All right, so we can do this. Anyone disagree? Any more questions? No, yes?
So you only recurse as far as you need to be along, right?
Yeah, so if I want to get at this char, I don't need to look at the thing in the string. So all I have to do is peel off the int card and get that, because we're no longer shadowing with this end.
Can you also explain a little more about how the static cast like reinterprets the memory of that location?
Yeah, so the way that the static cast does is with inherited types, the C++ language and the compiler know that when I have this inheritance here, and I'm static casting to a parent type, I can just look at the memory. This is pretty much how the memory is actually laid out in like my memory. I have my string, and I have my character, and I have my int, and they're all next to each other. So it just changes its perspective. Instead of looking all the way here, it's just going to look here. And the thing at the bottom then is this character. We're good? Yeah. Oh, I see 2 thumbs up over there. Awesome. So let's make that make tuple thing. Compared to the previous, this one's easy peasy. So make tuple. What did we say? It has to take any number of args, arbitrary, 0, 75, 42, 1. And it has to be able to deduce the template values, or the template types. We got to know, without having to say in the brackets int char string, that this here is a tuple of int char string we're trying to return. And then once more, this is that same make tuple code, or the same make tuple test. So we're calling make tuple, we have an int, a char string, and we're not telling make tuple int char string. It's going to figure that out. How are we going to do make tuple? This is the framework. First, we will declare a tuple with the types that it is able to deduce from the arguments. So from the args, it can say, because this is a function call, that I know what the types of the args are. I'm sticking them into my parameter pack t types, and over here I'm going to make a tuple with all of those types. I'm going to call it result, because it's the thing that I'm later going to return. When you make the tuple, you want to get the result out, the tuple that you're creating. Now, between making a tuple and getting my tuple out, I got to fill my tuple. I need to put all of those arguments where they need to go. Fill tuple is a function. And I'm going to show that in the next slide. But first, let's talk about the logic that fill tuple is going to want to go through. Think about it if I had just a list of things in an array that I want to fill. I might have a while loop that says, well, there are things to fill the first thing, and increase the index. So if I have an index at 0, fill the 0 thing, increase the index, fill the 1 thing, and as long as I have something to fill in there, keep increasing that index and putting it in. That's what our fill tuple is going to do. Notice over here, we have the result, the thing we're trying to fill, and the arguments, the thing we're going to fill in, and we're starting at this 0 thing. We're starting at the beginning and filling after that. So, here is the code for fill tuple. Let's look over here. Don't look there yet. It doesn't matter. We'll get there. We have the index. Where in the tuple are we filling? We have the type of the tuple. If I'm doing it with my tuple int char string, this is that tuple int char string. And then here, I have a first and a rest. When I call the fill tuple over here, what did I have? I had a tuple, the result, and I had the args. So over here, I'm going to have the tuple to fill, the result. Here I'm going to call it to fill because I'm filling it. I have the first arg, and I have the rest of the args. This is going to be that recursive pattern again, these list t's from 280. So how is that going to work? I mentioned in a while loop, we would say, put it where it needs to go with the indexed place. I have that get function we just wrote with the index. The get function is going to do all of that peeling off the cards, figuring out where I have to put that first, so that when I say get of toFill equals first, it puts this where it needs to go. when it's index 0, it's going to say, put it here. Index 1, it'll peel off that card, put it here. Index 2, it'll peel off 2 cards, put it here. And then I'm going to call fill tuple on the index +1. Start at the 0th position, do the 1th and then the 2th, and etc. with tuple and the rest. So that, yeah, I should have an example. Nope. Yeah, so when I'm filling the tuple in char string with, well, why don't I write this on the board? Yeah, so what did I call earlier? I called make tuple of 64 h and then a string with foo. So I have my make tuple with these. These are the things I want to put inside of my tuple. So what does I do first? First, I'm going to create a tuple. I see an int char string, so the result will be of type int char string. Starting at the 0th, I'm going to call fill tuple and start filling the result. So over here, 64 is the first, h and string are the rest. Tuple, my tuple to fill, let's say it's up there, just the tuple, is going to be my thing to fill. So I'm going to call get. I'm going to see that index is 0, I peel off 0 cards, and then I put my first element in there. So the int becomes 64. Or,
9,
I can put it over here.
4.
Oh,
That was, I thought it was 9.
Well, it doesn't matter, it's relevant.
There. Got to make sure they understand, David. So what am I going to do here? I filled the first, so I'm going to call fill tuple again with the index +1. 0 + 1 is 1, and the rest. To fill is still going to be the same. Why is to fill the same? Normally I've taken off that first thing and I've only had the rest.
Because you also use the same tuple.
Yeah, well, with this get function, when I call it with the 1 here on the to fill, the get knows how to peel off the cards. I don't have to start peeling things off over here. That would be redundant. I already have get to do that. So when I call it with then the first being h and the string being foo, the get function will take away that int card, put h in the char memory, and I'm going to do it again with the index +1. 1 + 1 is 2. Question?
So get IDX to fill returns a reference
Yeah.
to the value, so that's why you can assign it with follow-up.
Yep. It's going to be the return type of get, if you remember, is a reference to the type T.
Okay.
So it's going to be this position in memory right here when I call it with 2. The get will just say right here is where you put the string. And then that assignment is going to say foo goes here. Yeah. And then what happens then when my rest becomes empty? I've used this, this, and this, so rest is empty. Then I just go up to this base case, which has only the tuple. There is no first and rest elements, that's overloading. And it does nothing, so I return. I filled my tuple, this is the int char of the string, and then what I can do is just return it. Hooray! Yes?
Why do we have to do string, curly thingy, foo, or can I just do foo?
The reason I put the word string here is because if I only have the quotes, then it becomes a C string, which is denoted as a pointer to a character array. So it is actually a completely different type entirely. The equality operator would copy then the pointer, and it wouldn't copy the actual foo. It would just say, here's where it starts. Yes?
Using C++14, can you add an S after that and make a C++?
I could do that, and even more fun in C++14, where's my get? Yeah, I could get rid of this whole line and just put auto in C++14 as the return type. So once more, tell your professors, upgrade our compiler to GCC 4.9. All right, so we've got the make tuple, we got the fill tuple. Let's go over this example. I just went over that example. Do we have any questions?
Has that approach occurred to you, like, trying to construct your tuple that will take a variable number of arguments, just to initialize the value of the first one, and then pass the rest of the arguments over to the class.
I know if we were to have we can't have the Variadic thing in a constructor because isn't that broken? No, what does Mark say? Mark,
What was the question? Like when we're initializing a tuple, and if we define a constructor for a tuple, it takes a variable number of arguments, and then the tuple has value and has a base class, and it just initializes the value after the first argument.
I think if you look at the standard tuple implementation, you will find such a constructor.
So it does exist. We could, but that would be kind of complicated.
The issue is that you would have to repeat the type to do so.
Or we could deduce them in the function, right? So the function would deduce them and then you pass it on.
Sure, you could do it that way.
All right. Any other questions?
Talking about auto, like, how is auto different in C++ 11 than it is in 14? Why would that work in C++ 11 where it said just replace the return type?
Yeah. So the difference is in C++ 11, you cannot use auto to deduce the return type of a function. It's just not part of the language in C++ 11. C++ 14, that feature has been added. So that's why you can do it, because it exists now. Or it exists as soon as you get your professors to install GCC 4.9.
So 2019.
No. Just when C++ 17 is coming out. All right, so any more questions? We're actually like right out of time. It's 8:30. Jay?
Where are the dogs?
Where are the dogs? They're in a few slides. You have 3 more slides. So before we get to my dogs, let's talk about what we talked about today. I'd like to thank you all first for sitting in through the whole thing. This was an hour-and-a-half talk. I saw a few people left after the hour. But anyway, we talked about templates. Templates are powerful. Templates are fun. They let you do stuff with the compiler at compile time. Template metaprogramming lets you do math and generate other things at compile time to save you some runtime. It's really cool, but not but yet. Variadic templates let you do other cool things. They let you have any number of things. We can make a tuple only in C++ 11. Before we had variadic templates, there was no standard tuple because having those compile time variadic arguments, it wouldn't have worked well. This code, though. Okay, question?
Standard tuple takes a multiple type or single type. Is standard tuple required for single type or is multiple type? Yes, standard tuple takes any number of types. It's a proper tuple. Okay.
Yeah. So anyway, this code, while it was fun to write, and while we've been through the journey and we've elapsed and it was cool, is not necessarily the most efficient code in the world. The what do we got? The STL has its standard tuple, and that uses a different implementation. What was your name?
Daniel?
Yeah, probably along the line of what Daniel said. It was Daniel, right? Yeah, okay. Yeah. And then also, using a constexpr function, instead of doing all those fancy template things for math, the multiple cases, will probably make your code a bit more readable. And really, when you're writing code that has compile time considerations, readability is going to be a very significant factor. But still, this is fun. Go brag to your friends. I was told that apparently if you're interviewing at like fancy finance companies, they actually like to see that you can do some of this compile work. But I've never had to do that in an interview yet. So yay, tuples, fun stuff. The tuple, or templates are fun. The tuple implementation that I got, I tried thinking about it for a while in the shower once, but I couldn't get the whole thing. This guy called Nish, he wrote a blog post about it. It's not necessarily the clearest blog post. Hopefully this talk made it a bit more clear. But it basically outlines the tuple with the tuple elements and stuff that we discussed here. So I gotta give him credit. And Jay.
Dogs!
Yeah, so thank you very much.